inclined to answer some of the questions that were just raised. How about circular, and how can we split eco-design from V directives? Isn't that exactly about making sure that we, at the end of life, are somewhat efficient? So that's what I would like to talk about, and I hope it would be nice to check with you by the end of the session towards, there's a D missing there, towards self-disassembling products. Are we close to that? Is there anything that could allow us to use such label, and I hope you will agree we are improving. This is what it is all about, the circular economy thing, and I think it's a risky word. Circular economy seems like an excuse for reducing product lifetime even more, because we are going to close the gap anyway, we are going to recover those materials, so who cares that we are ever reducing that, that lifetime further. But this is what it is all about, and I'm sure you know this kind of schemes. What I would like to talk about is not so much the use phase, the energy considerations, not so much the repair phase, although also that could be facilitated, but also the biggest challenge, how about the ultimate end of life? Can we still, at that time, recover materials in a way that we can really talk about closing the circle? We all know the motivation for that, the idea, and these are some figures from people working very closely with the end-of-life treatment facilities like Umicore. The amount of materials in there make it really worthwhile. There's more materials in those historical landfills than there is in the mining ore where they originally came from. So that should be lucrative. So how good are we at getting them out? But this is very much what where the trouble starts. This is what we do. In Europe, we have legislation that obliges countries to organize a collection scheme, and this is what it looks like if you take, for example, the very polyvalent kind of waste of electronic equipment. We are collecting a lot, and we are mixing it, and it looks very much like this. Now, in terms of thermodynamics, what we are doing here is turning structure. That's what products are. We know products, we know what is in there, we know where we can find certain materials in the products, and we are turning that into chaos within seconds by just mixing it in this kind of environment. That's the second law of thermodynamics. We are increasing entropy tremendously fast, and we know it costs a lot of energy to undo that. So that's really making life difficult. The question is, could we do any better? Now, what is the effect of that? And these are numbers from Hagelugen. Christoph Hagelugen is a Umicore co-worker. So this is about gold, and this is about them, and them there is southern economies. These are examples from a country like Ghana, where we know there is fairly big effort to collect waste streams because people earn a living from that. They then treat those waste streams fairly intensively. With a screwdriver, they take apart products, and then the big trouble starts because then they don't have the appropriate technology to take out the gold and the copper and the other valuables, and they use leaching techniques you don't want to be near to. And that's where tremendous environmental issues also occur. The end result of all those efforts is an efficiency of about 20%. Now, if you look to Europe, if you look how we are doing that, I have to disappoint you because we are not doing too bad and we are improving in the collection schemes, but then we apply the techniques that I just showed you the snapshot of. We start mixing materials and we start treating them very crudely. Seems systematic, but it isn't very well optimized, and we have a very low efficiency there of taking out the materials. The electronics, they are not a material. They are all kinds of materials, and they go every possible way. They go with the plastics, they go with the steel, they go with the aluminium. So unfortunately, about only a quarter is going in the right direction and ends up at the gate of Umicore, where they can very efficiently take out the gold. They have an efficiency, depending on the materials, 95, 98%. If we add all of that together, we end up with an efficiency of 12% of the gold. So forget about closing the loop. This is what we are doing today. So we have to get a lot more efficient if we ever want to get close to the 20%, to the 50%, let be the completely closed loop, the 100% that we are dreaming of. So I'm going to try to tell you what is the state of the art, how well could we approximate that if we apply best available techniques, and that's mainly oriented to improving that second stage. We have the products, we have to pre-process them before the chemist, the metallurgist can actually extract the materials. Some decade ago, I got a bit fed up with the big dispute, should we go for destructive shredding for recycling or should we aim for disassembly? And for every occasion, for every example of a successful disassembly activity, there were at least two of people who would say, we tried it, it doesn't work. I remember automotive, at some moment, they said, really, we don't want to discuss disassembly anymore. It has been tried and it's totally ineffective. So we had a look at, this is a representation of 17 case studies of existing disassembly activities. We clustered them, we studied very extensively 25 different dimensions of those cases, and this is a map showing that 25-dimensional space in a 2D map. You can't see too much in there, but then we did some kind of clustering exercises. We found a cluster, fairly big one, that contained cases. They're all existing disassembly activities, so they need to have some kind of a profitability, I think, to sustain. Well, what did we find in there? We found products with a fairly long lifetime, like trucks, like photocopying machines, like medical scanners, big devices with a high residual value after many years of use. That was the first category. We had a special case in there. We had the Fuji reuse cameras. Well, not reuse cameras, single-use cameras that are being remanufactured and then get an extra lifetime. They are typically recycled or reused 5 to 6 times. They are historical devices, so now we had full information on them. Fuji released that. So that is a product designed to be demanufactured, to be remanufactured. Then we had a cluster of, I would say, medium value products like IT equipment, PCs in there, some household appliances that were being remanufactured, that were being refurbished for being sold for a second lifetime. And then the last cluster is a cluster with just disassembly activities for recycling purposes, trying to get the materials out. The numbers or the symbols I add here, they indicate the most important parameter, the profitability. The double plus, highly profitable business, ongoing business. You can get any spare part for trucks remanufactured secondhand. It's perfectly available. It's a thriving business. We found that the medium value, the ICT equipment, it was barely break even, often making slight losses, so it would end up in the non-profit sector. And then the last category, and that's the bad one, this happened to be an exception. Actually, it was a destructive shredding facility in the end, but with efficient material extraction. It was not really disassembly. All the real disassembly efforts for material recovery were losing money. They were kind of pilot plants, and they would typically shut down after a while. That's the starting point. Okay, so the big question now, what should we do? We go for shredding, knowing that we are going to waste lots of material, or we should go for disassembly, and we know then there is a profitability issue. So we had a look at what is now the core of the business, and I apologize for the complexity of this figure, but what does this represent? This is the take-back scheme in Belgium. We have 3 points where you can deliver your product. Shops, outlets, you buy a new product, you give back the old one. The collection stations, so the container facilities where you can get rid of your V products, and then the second-hand shops where they will try to find a new destination for your product. And our big question was, how much should we now improve the efficiency of disassembly before in this network, and we assumed that every player in that network was greedy. Every player would just look for his own benefit, for his own economic optimum, and would take decisions accordingly. So now how can we steer the product streams that most of the products would finally get treated with disassembly, taking out the most materials? So we just looked at time spent on that. We measured times. We calculated the cost. This is for a Belgian economy, so fairly high labor cost. And to make a long story short, with some linear programming modeling, we got to this kind of output. What you see here, 100% is the cost today to disassemble such a product. And you can see how much should that cost drop before disassembly becomes attractive. So how much of that cost should be removed before disassembly becomes the preferred scenario, overtaking from shredding, from very low-end material recycling. And you can see, well, we have 8 different product categories in there. For some products, it's totally infeasible. If you take an electrical water boiler, whether you shred it or you disassemble it, the output is about the same. There's no big benefit in that. There's no benefit at all, actually. So you would have to drop the cost with about 100%, and that's totally infeasible. But for high-end products, like washing machines, like computer systems, for example, well, you would have to drop the cost at least 65–70% before it starts getting a chance. So that's the challenge. We have to make this assembly at least 65–70% cheaper before economically this becomes the dominant scheme. So the big question is now, can we do that? We have had colleagues trying that, trying robotic systems, automation, really the most advanced kind of techniques, and finding out it's really hard. They would get reductions 10–20%, and they would be very happy with that because they knew how difficult it was to get there, and it's just not good enough. So 2 PhD generations ago, we started to think, how should we do that? And actually, I did a little exercise. These are 2 of my girls, 2 of my kids. At the time, they were still somewhat respecting their father, and I asked them to build a Lego house. And you know how this story goes. How much time does it take to build a house? They did it quite nicely, you have to admit, it looks like a house. And they spent about 20 minutes doing that. And then I asked them, and of course they got frustrated first, I then asked them, can you now take it apart? And can you do that structured with the materials nicely separated according to color and size and whatever? And there's a little clip behind that, but I'll save you the time. I think you know where this is going. The disassembly is easier. The disassembly is much faster than building the house. This is increasing entropy, and that's what systems naturally do. If you shake it well, it will fall apart. And that's so how come this is not true for our products? How come that building products we can do in seconds, and taking them apart takes minutes? We are doing efforts to overcome entropy evolution. So it's a mental status. I remember telling colleagues, say, now we want to make products that fall apart like this. And some of these colleagues would literally shiver. Like, I spent half a lifetime avoiding that. And now you want me to make a television that will fall apart when you do something special with it. So, okay, what is the problem? Every disassembly system that we have studied would typically use 1-to-1 disassembly. You put in a screw, you have to take out the screw. You make a spot weld, you have to drill open the spot weld. You make a glued joint, you have to break open that joint. That's very much the state of affairs we see today. We would like to get to one-to-many disassembly. One signal, one action that can deal with the whole product, and even preferably a batch of products. Just put a pallet of products in whatever facility and try to undo those joints collectively. That would probably allow a much higher efficiency. So let's see how far have we evolved in achieving that. It's nice to think like that and say, okay, let's do magic with products. If we all agree we can do magic, then the problem is solved. It's not that easy. So we baptized this thing extract, externally triggered active disassembly. And I must admit, it has taken us 2 generations of PhD students to make this to a mature level, but I think we got there. 2 approaches for this one-to-many fastening techniques. There is you all know some examples of products that are very easy to take apart, But it is because a designer was asked to do special effort for that. And that's what we call the disassembly embedded design. I'll show you some examples later. So a designer that says, okay, we would like a button. If you push the button, the whole product will open or will fall to pieces. Can we do that? Yes, we can. And how about active disassembly? There we would like this to be generic. So if you use the proper technology, if you use the proper joints, then it can be done without special further design effort. No direct physical contact, no designed system to really trigger these things, just an external signal. And that gets very close to self-disassembly. These are some examples of what we call the disassembly embedded design. So designers putting in effort, achieving easy disassembly. This is a typical kind of box enclosure for electronics, for your computer system, and you have all the snap fits linked together mechanically. You push the button and the cover will open. Can be done, but it takes effort and it takes probably some money. This is an example for a CRT screen. A cast-in wire, a nickel chrome wire, you put some current over it, it will create a thermal stress, and the CRT tube will break exactly where the different types of glass have been joined. So a little investment, a little effort, a little design precaution, and you can actually disassemble or separate materials easily. I think an example of Dell, within seconds you can open such a cover, you pull all the green elements, and indeed within so many seconds you can really take apart this computer. This has not been designed by Dell because of end of life. It's for maintenance purposes. It's for service stations. So we used to have such systems in our university. Students would come back, say it doesn't work, pull out a hard disk, plug in another computer, 1 minute, 2 minutes, and they are gone. They can be helped, actually. So they do that for service purposes, not for end of life, because it costs extra money. And now we get to this externally triggered principle. What kind of joints, what kind of technologies would allow us to facilitate this externally triggered disassembly? There has been a whole generation of efforts, people working with Shapememory polymers, Shapememory alloys, thermal effects. You heat up a product and it starts to behave in a certain way. Has been tested, has shown quite some disadvantages. You have to heat fairly high. You have to imagine what is the natural boundary conditions for such a product. If you ship a television set in a container, and that container is on top of the ship or is in the harbor in the sun, you get to 80, 90 degrees in the container. So you have to stay above that. If you have to go above 100 degrees, very quickly you start to damage electronics. So it's a delicate thing, and it takes time to heat, it takes energy, and afterwards you get stuck with a hot product. So you have to also take all of that into account. And also the Shapememory polymers that were used in there, they tended to be non-stable over time. They were not shock resistant, so there were a number of technical difficulties. We have limited time, so I'm not going to show you every clip in here, but perhaps I should show you this one. This was an effort by some industrial partners we have been working with. They worked actually with, let's see whether I can, I should, yeah, okay. So what you see now is a television being assembled with some tapes in between, produced by Onetoone, and those tapes are temperature sensitive. They are double gluing tapes. You use your television for functional lifetime, and after that you put it in some kind of an oven, you heat up, and the thing basically falls apart. Has been tested, Onetoone together with Philips, and they can actually do that. Functionally it works, but it still has the objections that I mentioned. Energy doesn't come for free. You need special facilities also to activate that. Every product would have to go into some kind of an oven. The next effort we studied, we observed, and we found quite interesting was some soluble nuts. If you have a bolt and nut connection principle, and if you can dissolve those nuts in some chemical environment, could you make it fall apart just by being somewhat patient? Patience is very much what is needed here. It's a slow thing. You don't also want those nuts to fall apart during functional lifetime, so you have to stay away very far from natural circumstances. Humidity are issues, and will this still work 10, 20 years from now? Some efforts to do that with electromagnetic fields. This isn't really the extract principle, because you would have to orient that magnetic field quite well, so it's not an external trigger really. Some efforts with bolts and nuts with electrical signals, so making the head of a bolt fall apart. Not an exact example of extract. And then this is the contribution we have been working on. We found pressure, a fairly interesting signal. Why? Because in our own environment, we are very sensitive to pressure. If you are asked to enter a room that is 1 bar up from your natural environment, you're in deep trouble. On the other hand, increasing pressure in a chamber 5-6 bar is cheap. Every pneumatic network can do that. We'll typically have a 7 bar pressure. It's cheap, it's fast, energy-wise it's not very expensive, it's clean, doesn't leave a history afterwards. So okay, we decided that pneumatic triggers were very attractive. And this was the first generation of designs that we produced, did some topology optimization, and this is the optimized design we ended up with, again, with colleagues at Philips. So you have to imagine this is about 3 centimeters high. And this was designed at a time that televisions were still about that thick. And you could have such snap fits in there. I remember asking these people, is this future-oriented? Aren't we going to get in trouble with your next generation? And their conclusion was, let's first walk before we start running. And so let's try this. But indeed, I'm again going to skip a few things and perhaps show you this clip. This is what it looks like if you put one of those pressure chambers into in a little vessel, transparent wall, and we just increase the pressure, and you can see it can be undone. You could use that for disassembly and then later on reassemble the same thing. You can do it a number of times. So, but again, this is about, the height of this thing is about 3 centimeters. So we found, okay, it's a good principle, it's just not very practical for the small snap fits that we have in mind. So that brings us to some mature developments, and this is just 3 years old now, end result of a whole series of developments that we did. And this is again one with pneumatic thing, but now we work with the foam. This is a foam here, a closed cell foam, and when we increase pressure it will indeed compress that foam. The kind of devices that you know, this is a little modem. So if you have to open this to get out the electronics, you're going to lose money on that. It will take too much time orienting, screwdriver positioning, opening 4 or 5 screws. This is the same thing put into a vessel. Now you see this is already the second stage. Here, to make it a bit more visible, we put in a piece of spring steel. So after the unclamping is happening, the thing opens automatically. This is, I hope you agree, very close to a self-disassembling product. And this is what you get out. In this case, with the shredding, that PCB would have been totally scattered. Over here, you just have to take the effort of sorting it, of putting it into the right basket. That was for the idea that we could help companies that would have perhaps a bond to their product. I'm thinking of companies like ICT, telecom service providers, network providers, that put these set-top boxes in your home. And at some moment they take it back because they are outdated, they have to be renewed, they have to be upgraded. Whatever they do with that box is none of your business, it's still their property. And they collect thousands of them. How do they treat them? Now this would be a way for very systematically either separating the materials or opening them for upgrading, for making the necessary adjustments. But you would still need, as a treatment facility, you would still need a dedicated setup. You still need a pressure chamber and a way of systematically handling the products going in there. So we were anticipating what with the real end-of-life treatment, where products end up in any possible facility, any possible treatment plant without special infrastructure, without special pressure chambers set up for example. So this is another generation of joints we have been working on, and the idea here was what can we do with the mechanical effort. So this is a principle where we use elastomers, very cheap material, and we had as a challenge in mind, what about force? What about the mechanical force, but the force that is sustained over a long period? If I think of my television, if I put a force on it and I pull for whatever, 5 seconds, am I allowed to take apart my television? Would you allow your kids to do that? And would you blame them for destroying the TV? Or would you just say, yeah, if you do that, then the intention was to take it apart? So that's what we have been studying. This is a joint. If you just have a big force shortly, it won't achieve anything. And I'll show you later that indeed this can be done. But if you sustain the force sufficiently high level, sufficiently long, you're going to pull apart the TV without a screwdriver, without any special devices. Okay, that's the principle. And so we calculated these things. The theory was nice, and this is what the prototype looks like. This is made in some backyard job shop, so very primitive prototyping, and we mounted it on some televisions, again, together with our preferred TV developer. And this is the elementary functional test. If I put a force on it for a number of seconds, can I make sure that the thing is not destroyed if the force is at reasonable levels? So still has to be a back cover that serves its purpose, protecting your TV. That's the first test. That's the functional life. Second consideration, how about rattling? How about noise? I ever bought a TV that was put together with screws and that really at low noise frequencies would start to shiver. That's not a good sales argument. So this actually helps. This kind of joints, they actually help to do that. This is a drop test. These are standards. If you sell products, they have to survive certain mechanical loads. So we just, in the packaging in this case, we tried all the different tests, vibration test. If you're driving with a TV in your truck, the Belgian cobstone roads, is your TV going to be disassembled as a result? No, it isn't. And now the proof of the pudding is in the eating. This is the conventional disassembly. Conventional disassembly with a screwdriver. That's the reference. It was speeded up, but it takes more than 2 minutes to open a TV. Now, similar category of TVs with the special joints, the elastomer joints. And this is a non-trained operator, just trying with the sizzle he has available in the workshop, trying to open this. Once he has a grip on it, he can actually open that TV very rapidly. You can see the next joints are really not of his concern anymore. He doesn't have to position them. He just 40 seconds. That's a real-time measurement that you saw. Statistically, so 70% reduction. Okay, that's within the scope of what we had in mind. At least 65-70% improvement. That's an experienced guy doing exactly the same thing, knowing this kind of system, and he only needed 12 seconds. So he went down 90%. Of course, I hope you agree with me, for your TV, this might be okay. If the dashboard of your car can be pulled off like that, if it's parked in front of the hotel here and some guy wants to steal your radio and takes out the dashboard as a compensation for that, you won't be too happy, I think. So there are products for which this is perfectly acceptable. There are other products where we would need adjusted version, but the idea is there. It can be done. And that's what I wanted to end up with. We did a lot of developments with Philips. Philips TVs is not Philips anymore. It's now TP. It's a Taiwanese company. If you buy a Philips TV, it's made by a Taiwanese company, and there is not a share of Philips money in there anymore. Philips was interested in the visionary aspects of eco-design. I had some of my graduates working there, and it was fun to see some of them winning prizes for green TVs. And at the same time, and it shocked me, at the same time they would state that the expected use life of TVs, Philips used to have a policy that for 10 years they would guarantee spare parts and access to services. They said we don't need that anymore because the average TV now is only used for 7-8 years. People accept that. And we expect the lifetime to go further down to 5 years. And they were happy telling that. Because growth and successful companies, we need to sell more TVs. We want to make a green TV, but we like to sell more of them. That's very much the catch. And the whole idea of product life extension and maintenance and warranty strategies, well, as long as we are not obliged. Okay, that was Philips. Now, TP. The logic, these people told us, they had some rights on some of the results, yeah, said, we are not going to use that. Yeah, because it's going to cost us some money. If we have to enter special snap fits with foam structure, if we have to enter even the very simple elastomer rings that you saw, they cost barely anything. They cost a few euro cents. And you have to put them in during assembly. So the efforts for the designers are almost zero. The investment is almost zero. Instead, almost zero is too much. If you ask us to spend €1 for a product, and we are going to sell 100,000 of them, that's 100,000 euros. Who is going to pay back that to us? If there is no demand, if there is no difference, end of life, say, hey, this is a Philips TV. They get exemption from eco-tax because they did an effort to make the product retrievable. If there is no such reward, then we are not going to be the ones doing the end-of-life treatment. So we have no return of investment. €1, even €0.50 is too much money. So that's the challenge I think we have. How can we now get to Eco Directive that says this kind of things exist, this is possible, and it's your responsibility to make sure you prove end of life is easy. If you can't prove that, you're going to pay for the treatment. You're going to pay for the eco tax. Thank you.
Thank you very much, Joost. Great presentation. And I just want to say one question before we go to coffee. I know you also looked at potential standards for time, etc. So what is your quick answer? Can we regulate some of this stuff under the Ecodesign Directive?
Yeah, we found, for those who are not informed on the WE directive, today this is very much weight fraction or a steered kind of system. You have to recover at least, depending on the category of products, 80, 85, 90%. Some of it can be with energy recovery, and there's a weight target. Now, shredding and separating steel and aluminium and plastics, whatever, allows typically to get there. It's a bit challenging, but the basic shredding techniques allow to do that. But the electronics, they don't weigh a lot. The gold is negligible in weight. So the money is thrown away like that. And also the impact avoidance opportunity is totally ignored by just going for the low end thing. So we have been thinking what could be another way of putting targets that would take that into account. And we came up with at least one possible strategy, that is for every product category, based on an LCA, based on a life cycle analysis, we could actually identify where are the delicate points. For some products, it may be the battery that has to be taken out. For others, it may be for flat screens, you have to prove that the electronics can be taken out, and there should be a target. Like the electronics, can you prove that you can access the PCBs in not more than, just call a number, 1 minute? Can you prove that you can get there? Can you do the effort? Is it a button? Is it an elastomer joint? Is it a pressure chamber? Is it a special tool? That's your responsibility as a designer. Prove that you can get there in not more than 1 minute. And then, of course, that 1 minute needs to be clearly defined. Not how long does a minute take, but how do you calculate that? How do you prove that? Is that some supervised test? Is that a video clip that you can submit showing that and not being cheated on in playing it too fast? Or could you have a time and motion study? And we have been working on that. Can we develop methods that would allow, we don't want to sacrifice products, we don't want to say do it 5 times and then we believe you can do it, because you sacrifice 5 products. So we have been working on the standards that could support
so
such
a time-related standard is possible.
Yeah,
okay.